Yep.
Can you hear that?
Can you hear that?
Yep. Thanks, bye.
And then she turns it off.
Just push the button.
This one?
Yeah.
So once I'm done, I push that off, and then she's on.
You can leave it on if you want. They don't interfere with each other.
Oh,
They're on separate channels.
that's nice.
They mix. So. Yeah, maybe that's what that's for. Maybe that's somebody's hair. Like it's somebody's head, yeah. You don't want to reuse that.
Welcome to our seminar series for 2017. Today it's my pleasure to introduce Dr. Natasha Dimova. Natasha did her master's at University of Sofia and her PhD at Florida State. Natasha and I actually intersected for a couple of years maybe at Florida State, and she moved on from Florida State in 2010 to work with Adina Payton and Swarinsky at Santa Cruz. And in 2012, she started her current job as an assistant professor in the Department of Geological Sciences at University of Alabama. And Natasha has been actively involved on doing some coastal work here, and she also teaches some interesting classes that might be of interest to our students, looking at tracer and hydrogeology and techniques in environmental radioactivity. Her most recent work has been actually all over the place, but some of it has been in the Arctic, looking at groundwater flow in Arctic lakes, and one of their latest papers was published in the proceeding of National Academy of Science on methane transport from active layer to lakes in the Arctic using Toolik Lake. So Natasha by training is an oceanographer, and the interesting fact that you might not know about Natasha is that she gets seasick.
Oh gosh.
I think Dr. Dindo and I have had very interesting conversations about Natasha sampling at the coast, but it's always been a pleasure to work with her. Without further ado, Natasha.
Thank you. Yeah, I was told I was in some sort of blacklist that I'm not allowed to go offshore. I'm really happy to be here. I feel this is more of my family than my own geology department, where I have to encounter structural geologists and petrologists all the time, and even the word cost and oceanography, which I started actually teaching intro to oceanography for non-majors in my department. When I was hired, it was sort of the forbidden word. You don't say, you have to talk only about geology, hardcore geology. But we are trying to sneak in some coastal work there. And believe it or not, we've been in your backyard pretty much all the time without you knowing about us. And what we are interested, of course, is to look at the impact of groundwater to the coastal areas of Alabama. And this particular work has been mostly done by my PhD student, Daniel, who is right here. And so if you have any tough questions, please ask Daniel, not me. I'm just presenting the work that we've done. Another thing that I want to say is this is 2 years of work we've done, but it's still not complete. So we have 1 more year of sampling. And so the data that you're going to see today and the estimates about nitrate and nitrogen fluxes delivered by groundwater are not final. So this is sort of what we've got so far. Okay. And before I start talking about nitrogen loading through groundwater to Mobile Bay, I want to bring your attention to my lab, which I had in the past 2 master's students who worked also in the coastline. We looked at saltwater intrusion actually in coastal Alabama with Nathan Coburn, who is now in the Army Corps of Engineers. John Ellis worked on groundwater discharge to coastal Alabama too, and he basically, I'll show you some of his cross sections of the current state that we know of the aquifer system in this area. And currently, so Daniel is working in Mobile Bay, and his work is I will be presenting today. My new student, Will, started working on a couple of different projects, not related to groundwater, which we a little bit got tired of. So Will is going to look at suspended particle transport through the Mobile River Basin down to the coastline in terms of heavy metal fluxes. It's something I talked to some people yesterday are interested. And so these are the current projects we have. As I said, Will is going to look at heavy metals carried by suspended particles. We have also a project that we just got funded by the Alabama Water Resources Institute with Auburn, and we're going to look at the relationships between groundwater-derived nutrients and institute-produced nutrients and sediments, and the rest of them are projects related to groundwater in different places. As Bazat said, we've been all over the place in Spain as well. Our lab uses as a major tool radioisotopes, naturally occurring radioisotopes. So we are involved in quite a bit, and will be more involved in sedimentology work. So we are doing lead-210 dating in sediments, which will be a large part of the sediment transport project to look at historical depositions of heavy metal fluxes along the basin and down in coastal Alabama. Okay. So motivation for this work, that's what we write in our proposals, right? So before I came to Alabama, the hydrogeology group in my department has been looking at nitrate contaminations along in coastal aquifers. And so what Jeff Tick and his student, Dorina Margulet, have seen is very, very high concentrations of nitrate in coastal aquifers. And so coming at the department as a coastal person, I started looking at what's the situation in the coastline, and this is a map, probably not absolutely correct, but it shows you more or less the problems we have in Mobile Bay related to Jubilee's events, and particularly the east coast of Mobile Bay. And the yellow color here indicates less persistent events, and the red one is events that happen on a regular basis. So having the information from coastal hydrologists about high nitrate and persistent high nitrate in the aquifer system with those events, we thought that perhaps groundwater might play some role in initiating this jubilees. And so that followed of some papers that were produced here at Dauphin Island Sea Lab by Justin and his advisor and McIntyre, and including my later Bazat and my former advisor from FSU, Bill Burnett, who started thinking that there might be really a link between the algal blooms that they see not only in Mobile Bay but in other places along the coastline with enhanced groundwater discharge. And there are some connections that have been made. But until I think Bill Burnett's work in Little Lagoon, there has not been direct measurements of groundwater contribution, particularly to Mobile Bay. So that's what we are trying to do. So as hydrogeologists, now we put the hat of the geology department, we first start looking at hydraulic gradients, and there are maps produced by the Geological Survey of Alabama. It's one of them. And blue arrows here show potentially groundwater pathways or flow directions based on hydraulic gradients, which are a result of water table elevation and topographic gradients. So this would give us more or less the idea of what the direction of groundwater flow would be, potentially. Right? And so from this map, again, what you can see is that we have steeper gradients in the east side of the bay compared to the west side of the bay. So that not necessarily means enhanced discharge, because groundwater, the other factor that has to be accounted is permeability of the subsurface and the sediments underneath this. So you might have the gradients and still don't have much higher discharge. And so we started looking, my first student, John Ellis, started looking more closely and combining data and information about a coastal aquifer system in the area. And it has been, this is not the first schematic that presents a coastal aquifer, but it's the most updated. So the aquifer in the area is consistent of 3 separate aquifer units, which are the A1, A2, and A3 aquifer. A1 and A2 aquifers are considered more or less the superficial aquifers here. And based on data that John collected from tracer data, we have firm evidence that the 2 aquifers are connected. And then we have more or less clay layer separating A1 and A2 from A3, which is the deeper aquifer, and it goes up to 100 meters depth. So A3 is isolated from A1 and A2. That's what our data shows. Particularly for Mobile Bay, we suggest that the groundwater that discharges to Mobile Bay is mostly from the superficial aquifer from A1 and A2. And this goes again down to 50-meter depth. And we don't think A3 particularly contributes to the water discharge to the bay. And I will show you why we think also that. So the questions we're trying to figure out, so again, going back to the HABs, the harmful algae blooms, is assuming harmful algae blooms are nutrient-driven, what is the contribution of groundwater to the nitrogen going to the bay? We know river brings a lot of nitrate, most of the nitrate, but we want to see what's the role of groundwater in that sort of budget. And yeah, we want to compare this to the river delivered nutrients. And a question that most people are concerned about is if this is a significant contribution, what the source of this contamination potentially in the aquifer is. Okay, so how do we do our groundwater measurements? As I mentioned, my group is using radioisotopes as our working tool. And so particularly to estimate groundwater discharge to surface water, we use an isotope, naturally occurring isotope, radium-222, which is part of the uranium-thorium decay series. It's direct daughter of radium-226. And radium-226 is part of the composition of the bedrock of the aquifer that makes up the bedrock. And so as radium-226 decay, which is in solid state, it will release this radium-222, which is a gas. It's inert gas, and this radon will then dissolve in the pore water or groundwater surrounding the rock. And as groundwater flows through the aquifer system, it will pick up this radon gas and potentially deliver it to surface water or the ocean flowway discharges. So if you had a way to measure, on the other hand, surface water has, the concentration of radon in surface water is very low or almost zero because the source radium is not in there. It's part of the aquifer. So you have this very large contrast between groundwater having extremely high concentrations, 2 to 3 orders of magnitude higher in groundwater compared to surface water. And that is a great tracer because if you have a way to measure radon in surface water and you see high radon concentration, you automatically assume it's coming from groundwater because that's the only source there. And so we do this, and we have this wonderful instrumentation where we can put it on a boat when we can get on a boat, or we send students. And You can actually drive the boat along the coastline and continuously measure radon concentration in surface water, and when you see a peak again in radon, that would be an indication for groundwater input. And we did this multiple times in Mobile Bay. This is one of the maps Daniel produced. Again, red colors show high concentrations, and lighter colors are lower concentrations. And this is the first step in our systematic approach. The next step is, once we have figured out where the discharge is, we want to know how much of that is. And so the same instrument can be set up in a stationary, and we have done this at 3 different locations. The stars indicate the time series we have deployed multiple times. And you measure continuously radon in groundwater, in the surface water again, which is your surface water end member now. Then you also sample the groundwater and measure radon in groundwater. And through a mass balance, you basically figure out how much is coming solely from groundwater. You would have some contribution from diffusion from the sediments. You have to account for the decay because all of them are radioactive, both the parent. You would have some radium dissolved in the water that you have to take into account too. At the end, you end up with some excess flux of radon that comes from groundwater. And when you divide this flux by the radon concentration in groundwater, your groundwater end member, you will get water fluxes or discharges in centimeters per day, or some sort of length per time. Okay? And so that's one part of the study. So we wanted to know where it occurs, how much, and the next question we want to know is where does it come from? I just showed you the map of the aquifer system, and I told you that we assume it's flowing through the A1 and A2 superficial aquifers. But we needed to verify this, at least for 2 reasons. One, because we needed to prove that it's the superficial aquifer is the source. The second is we need to have very good representative of our groundwater end member, because from what you see from the calculations for flux, the groundwater end member plays incredibly large role in the final estimate. So we really need to make sure we are sampling that groundwater plume that we are assuming is going to the water. And the way we do this is using a shallow geophysics technique, which is co-electrical resistivity. So this is basically a cable, as a snapshot of one of our images. So you place the cable on the ground perpendicular to the shoreline. So this is land, and part of the cable most of the time is even underwater. So the black dots that you see here are electrodes, and we fire electrical signals through these electrodes, which transmit in the subsurface, and the receiving electrodes would measure the voltage differences and give us resistivity, total resistivity distribution in the subsurface. And so the way to read this image is that the red colors here are high resistivity, that assumes fresh water, and the blue colors are low resistivity or high conductivity. We always think of conductivity, but just have to think exactly the opposite, which is the blue color, and that would be perhaps brackish or seawater that conducts most of the electricity. And so what you can see here from this image of shore perpendicular snapshot, you will see very clear, large red plume, which indicates the fresh water, groundwater fresh water getting to the ocean floor and discharging there. Okay, so based on this, and we also can tell how deep this discharge occurs based on our vertical scale. So you can see that in this image we hardly go further 30 meters, 35 meters the most. And if you remember, our A2 aquifer, the boundary was at 50 meters, and the deeper was at 100. So this, we are very confident that indeed the discharge to this area occurs mostly in the superficial aquifer. Okay, so some results. These are just examples of the multiple surveys, radon surveys that we did. And starting with our first survey, one of the first surveys in March 2015, you definitely see much higher radon concentrations on the east side of the bay compared to the east side, to the west side. I'm sorry. And so we did this also in July 2015. So to compare, for us, March was the wet season, where we had most of the precipitation. Groundwater mostly is driven by precipitation. So we wanted to see whether that pattern of higher discharge and higher radon would repeat in the dry season when we don't have that much rain. And although the concentrations were much lower, so you can compare March versus July. So the highest we got is in the dry is about 3 dpms per liter, sort of some unit for activity concentration. And in March we had 11. We consistently saw higher discharge in that side of the bay. So what about resistivity? So interesting thing, which is not surprising, is that because the discharge happens in the superficial aquifer, is that most likely this discharge will be tidally modulated. The tide, so we did time series. Again, this is a place where we place the cable in short perpendicular fashion. And so we basically took a snapshot through falling tide, which is the top plot that I'm showing. A, B, and C are different times during falling tide. And so what you see is this red plume of fresh water is getting larger and larger as tide goes down. And that's normal because as tide retreats, pressure to the aquifer is released and more groundwater is discharging. Then you have high tide. This is going to push this freshwater plume back into the aquifer, and it will shrink again. And you will see this pulses of groundwater with tide cycle. So we call this in our coastal oceanography community tidal pumping, and probably some of you too. So tidal pumping is one of the mechanisms triggering groundwater discharge in these areas. And based on experience that I had and many other people who have been using this same technique, is the larger, of course, the tide range, the larger the fluxes are that would trigger this flux in and out. Okay, so the reason we did this also is that, remember, we wanted to be very confident of our groundwater end member. So what we did in the second year of this project is installing short perpendicular transect of piezometers on both sides of the bay. So this is showing images, resistivity images from the east side, from here. So we have 5 piezometers, and they range from 3 meters depth. This is somewhere on land. This is in the tidal zone. We have 3 different depths, 3 piezometers, and then we have one which is in the water. And so when we sample for nutrients and radon, we sample the plume that we assume, excuse me, is discharging into the bay. And so we also recover the core from the deeper well, which is on land. And this is sort of a profile, and Daniel did very thorough sediment characterization. And we wanted to look and try to figure out the hydraulic conductivity and permeability of the layer, the different layers. And what we saw is that we had a top fine sand, which is basically the beach sand, up to 50 centimeters. And then we had this very large B layer, which is fine sand with a lot of organic material, which we found it's about 40% by weight of this layer, which had very low permeability. And then the one that we think is basically, which serves as a conduit for groundwater with the higher permeability, is the D layer, which is at about 3 meters depth. So same thing for the west side. So you see the resistivity image is here completely different. I remember that in general we didn't see a lot of radon there, so hydraulic gradients are also not as steeper as on the east side. That assumes that we expect to have less discharge there. And the image shows basically we have fine sand again on the surface, which is the beach sand. Then we have these very low permeability gray silt, and then we have again a layer of very fine sand, which has high permeability. So we have very permeable surface layer, then we have this blockage of very thick layer that has very low permeability, and then we have the sand again with high permeability. Same sediment analysis. And so although C has very high permeability similar to the east side, we don't think that could play as a conduit for groundwater because we had the B layer, which has much, much lower permeability, which blocks the infiltration of rain, eventually groundwater, through the sediment. So we assume in this place, if there is a discharge, it's really in the very top layer. It's almost surface runoff, which is through the A layer, which is the beach sediment for us. Okay, so we did all that work. We deployed multiple times our time series on both sides of the bay. And so we did, as everybody tries to do, some sort of seasonal study and figure out patterns and both sides. And so this is our data. On the east side, the radon mass balance show during the wet season that we have about 27 centimeters per day seepage rate, and during the dry season is about 16. Whereas on the west side, we have much, much lower discharge, about 6 centimeters per day during the wet season, and not that lower during, it's about 5 during the dry season. So how do we how do we convert this seepage rates in centimeters per day in volume of water per time? That's in order to compare what is the contribution volume-wise of groundwater versus the river. The river is in cubic meters per day, so we need to convert this in cubic meters per day too. So for that, we use again our resistivity images, and what we do is trying to figure out what the seepage phase, the size of the seepage phase on each side is. So we have a shoreline, say on the West Bay, of about 35 kilometers, and the plume goes about 100 meters offshore, so multiplying this surface area by our groundwater fluxes, that would give us total discharge in volume per time. Do you guys agree? And so for the East Bay, we got about, in the wet season, about 9 times to the 5th cubic meters per day, and a dry season, almost half of it. And the West Bay, as you can see, not much of a difference, but in general, overall, much lower than, obviously, the east side. Okay? And so this is how we calculated it. I just explained it to you. And so to figure out how much is this compared to what the river brings, we need to have estimate for the river discharge. And while we can handle our groundwater, it turned out that determining discharge from Mobile River was quite challenging because we really don't have good gauges to do that. And if you guys know of something that we can, use, please let me know. But basically, during the same time we did our groundwater study, we also sampled Mobile River and Tanza River at these two locations where USGS has gauges, and we can retrieve some data for river discharge. And what we did is we just, add together the two numbers and assume this is what reaches the bay. Whether that's the real scenario, I'm not confident about it, but we don't have a better estimate for the river discharge. And so again, we also sampled nutrients so that we can calculate nutrient fluxes through river discharge, and then eventually with the nutrient data from groundwater and the groundwater fluxes, we can compare the two fluxes and see how they look like. So, and we did this, and so we calculated that, if you remember, the total groundwater flux, if we add the East and West Bay together, is about 1.3 times to the 6 cubic meters. During the same time, the river is this number, or just to remember in your head, is during the wet season, the groundwater contribution is only 2% of the water flux to the bay. And during the dry season, it is less than 5%. So very small amount of water getting from groundwater to Mobile Bay in terms of water fluxes. So what is more interesting for us is to figure out what does this groundwater brings and how this compares to the river fluxes. And so the way we did this is, again, say we take an average concentration of nitrate in groundwater in the East Bay, and we have the discharge. We multiply these two numbers and we get nitrate fluxes. And we did this for the wet and dry season for East and West Bay, and combine the two numbers together, and we calculate also nutrient fluxes for the river. So what we found in terms of specifically nitrate fluxes is that during the wet season, groundwater delivers about 4.6% of the nitrate. And this is during the wet season. During the dry season, the number is slightly higher, almost double, 7.7 or 8% of the river contribution. So we also did analysis for other nitrogen speciations. So I just gave you the numbers for nitrate. In terms of ammonia, though, if you look at the numbers during the wet season, it's insignificant. But during the dry season, 52% of the ammonia is coming from groundwater. And if you guys remember, the number for the water flux is less than 10%. So that's significant contribution, we think. We also did analysis for DON, and those are the numbers, preliminary numbers that we have so far. And so if you look at the total nitrogen to the bay delivered by groundwater, it's about 10% of the total nitrogen, and half of it is ammonia. So, and we can talk about this and why that is. But the last thing I wanted to show here is the question, the third question in my first slide was, where does this particular nitrate, which was big concern. And something that actually we changed mind through this study is that, remember back in time, back before us, people claim nitrate is the player, is what groundwater brings to the coastal areas. But numerical modelers, when they do the nitrate fluxes, they usually sample deeper wells. And we did this the first year. And the nitrate in the deeper wells is much, much higher compared to the shallow wells piezometers that we install at the beach. And so once we switch N members to the piezometers, that we were confident this is the water that gets into the bay, the ratio between ammonia and nitrate completely changed. And you saw the picture. But we had in mind of doing sourcing of nitrate anyways. So what we have seen from all the samples that we've done so far is most of the nitrate that eventually gets to the bay is nitrate from nitrification from soils, which confers with the study that Margulet and Teague did. But they basically sample just the deep wells that Geological Survey has, and they're going deep into the deeper aquifer, which is not really the N member you should consider when you do your nitrate fluxes. So one thing, I guess, what so far is interesting for us is that people also claim that nitrate going to coastal Alabama is mostly from sewage, but we did not see really a lot of data falling into this range. And that may change because we have one more sampling year, but at that point, our data is mostly concentrated in this area. And so what is next? So I've been thinking recently about the composition of groundwater that reaches the coastal areas and whether that is determined and dominated mostly from infiltration further on land, or the water that discharges in the coast is combination of some geochemical transformations that happen in the sediment. And we see doing this sediment analysis opening our eye, especially when we did organic component contribution, this thick layer that we see of organic matter we think plays an important role in the final composition of the discharge water to the ocean floor. And something that I've been thinking of looking more, and Bazat has been much more working on this, is to try to figure out how much of it is land-derived and how much of it is in situ produced into the sediment. So the picture of this can change completely. That's all that I have. Thank you.
Question for Natasha?
Or for Daniel.